Welcome to the next session. Now we were discussing types of singular points in the last session. Maybe at the end of the session we have finished our removable singular point, right? Now we go for second category of singular point, that is pole. This is very important for our complex variables and contour integration. Pole. Suppose we have a complex valued function f of z and z0 is one of its singular point. We say that this is a pole of this function f of z. If the Lorentz series expansion of f of z about z equal to z0 has finitely many terms of the form 1 by z minus z0. So in case of removable singular point, we should not have any terms of the form 1 by z minus z0. But in case of a pole, you must have finitely many terms. That means you may have only one term or two terms or 1000 or 1 lakh or 1 crore, but you must be able to count how many terms are there with the form 1 by z minus z0. Finitely means countable number of terms of the form 1 by z minus z0. In this case, this is called a pole of this function f of z, and the highest power of 1 by z minus z0 is called order of the pole z0. So order of poles are very important for us. Let me recall this definition once again. We have a function f of z, complex valued function, and z0 is one of its singular point. We say that this is a pole of f of z if the Lorentz series expansion of f of z has finitely many terms of the form 1 by z minus z0. Finitely many. You may have exactly one term or 7 terms or 1000 or 1 lakh or 10,000 crores, but you must be able to count how many terms are there of the form 1 by z minus z0. If you are able to count the number of terms of the form 1 by z minus z0, then your job is over. Then we say that z0 is a pole, and whenever we discuss a pole, I must know what is the severity of that pole. So that severity is given by highest power of 1 by z minus z0. Okay. In that case, this is called a order of the pole z minus z0. The highest power of 1 by z minus z0 is called order of the pole z minus z0. First write the definition and then we discuss an example. Let z0 be a singular point of a complex valued function f of z. Let z0 be a singular point of a complex valued function f of z. Let z0 be a singular point of a complex valued function f of z. Stop. If the Lorentz series expansion of f of z, about z equal to z0, has finitely many terms of the form 1 by z minus z0. If the Lorentz series expansion of f of z has finitely many terms of the form 1 by z minus z0, then z0 is called a pole of f of z. I think this point is very clear. And the highest power of 1 by z minus z0 is called order of the pole z0. Now we discuss an example. Suppose we have a function f of z equal to e power z by z power 4. Now when you replace z by 0, the denominator gets 0. That means 0 is a singular point of f of z. 0 is a singular point of f of z. Now let us go through series expansion of overall expression. Here f of z is 1 by z power 4 into the series expansion of e power z is 1 plus z square by 2 factorial plus z power 4 by 4 factorial plus and so on. Now multiply with 1 by 4, this becomes 1 by z power 4 plus 1 by z cube plus 1 by 2 factorial into z square plus 1 by 4 factorial. This is I have missed z cube by 3 factorial. This is z cube by 3 factorial like this. Now 1 by z power 4 plus this is 1 by z cube plus 1 by 2 factorial z square plus 1 by 4 factorial into z plus and so on. Now when you look at this series expansion, actually this is z power 4 by 4. Let me write one more term. This is actually z power 4 divided by 4 factorial plus and so on. Plus and so on. Now when you divide with the z power 4, here in this case the term becomes, this is 1 by 3 factorial into z plus this is 1 by 4 factorial plus and so on. What happened is the first term is 1 by z minus 0 whole power 4, 1 by z minus 0 whole cube, 1 by 2 factorial into 1 by z minus 0 whole square, 1 by 3 factorial into z minus 0. From fourth term onwards, we don't have z terms in the denominator part. So how many 1 by z minus 0 terms are there? 1, 2, 3 and 4 only. So 4 is countable. Therefore, in this case, once I go through series expansion of e power z by z power 4, I have only 4 terms of the form 1 by z minus 0. This is 1 by z minus 0 whole power 4, 1 by z minus 0 whole cube, 1 by z minus 0 term, second one, third one, fourth one. We have only 4 terms of the form 1 by z minus 0. 4 is finite value. Therefore, here 0 is a pole. But what is the highest power of 1 by z minus 0? 4. Therefore, here 0 is a pole of order 4. Therefore, in this case, 0 is a pole of order 4. 0 is a pole of order 4. So, first write all these points. Here is singular point. That is essential singular point. Shortly, we call it as ESP. Suppose we have a complex valued function f of z and z0 is one of its singular point. We say that this is an essential singular point of this function if the Lorentz series expansion of f of z about z equal to z0 has infinitely many terms of the form 1 by z minus z0. You can easily remember the sequence. See, when we started with removable singular point, we have 0 terms of the form 1 by z minus z0. Basically, it's a drawback, but that drawback can be eliminated by going through series expansion. In case of pole, z0 is a drawback, but how many drawbacks are there? Only finitely many drawbacks. Drawback means singular point. But in case of essential singular point, it's a drawback, but you must consider it. Because even if you go through series expansion, still you have infinitely many terms of the form 1 by z minus z0. Let me explain. In case of RSP, no terms means 0 terms of the form 1 by z minus z0. In case of a pole, we have finitely many terms of the form 1 by z minus z0. In case of an essential singular point, we have infinitely many terms of the form 1 by z minus z0. See the difference. The sequence is very simple. Always I need to go for series expansion. If I don't have any terms of the form 1 by z minus z0 after series expansion, it is called removable singular point. In case of pole, it has finitely many terms even after series expansion. In case of essential singular point, it has infinitely many terms of the form 1 by z minus z0. So whenever the Lorentz series expansion of f of z about z equal to z0 has infinitely many terms of the form 1 by z minus z0, then we say that z0 is an essential singular point of this function. Let us take an example. Suppose f of z equal to sine 1 by z. Now in the denominator z is there, therefore 0 is a singular point of f of z. 0 is a singular point of f of z. Now let us go through series expansion. So this is sine 1 by z. Now when you take series expansion of sine z, actually it looks like this: z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial plus and so on. This is the series expansion of sine z. But I want series expansion of sine 1 by z. So therefore replace z by 1 by z. In the series expansion, replace z by 1 by z. This is 1 by z minus 1 by z whole cube divided by 3 factorial plus 1 by z whole power 5 by 5 factorial minus 1 by z whole power 7 divided by 7 factorial plus and so on. Now when you go through this, we have infinitely many terms of the form 1 by z minus 0. So it comes to denominator 1 by z, 1 by z whole cube, 1 by z whole power 5, 1 by z whole power 7. So we have infinitely many terms of the form 1 by z minus 0. Therefore 0 is an essential singular point of this function. Why we named it essential means you must consider. See, suppose a singular point is a drawback of a function. See, suppose when you look at function, compare function with human beings. So generally human beings have drawbacks. Suppose there are 3 types of persons. Every person will have their own drawbacks. But if the drawback can be eliminated by giving some suggestions, if a person has if a person has free from the drawbacks, then we call them as good persons. Every person will have drawbacks. So here drawback is nothing but singular point. Always compare function with human being. Singular point means a drawback of a human being. So I am giving some suggestions. Here I am going for series expansion. If a person gives some suggestions to a person who is having drawbacks, if drawbacks can be eliminated, then those persons can be called as good persons. Now when you look at false, people will have some drawbacks. But even if they get some suggestions, drawbacks can be eliminated, but all drawbacks cannot be eliminated at a time. Still some drawbacks will be pending. So in that case, they will be called as average people. So they are neither too good nor too worst. But when you look at essential singular point, people will have drawbacks. Even if you give any number of suggestions, n number of suggestions to those persons, you cannot eliminate even single drawback. Such persons are called bad persons. So you must consider their drawbacks always. Okay. First you need to give chance to the bad persons. If the persons have some drawbacks, generally they will be called as bad persons. Generally, this is just for a funny point of view, not in general. Okay. So if a person has some drawbacks, we call them as bad person. So how to remove their badness? By taking some action on them or by giving some moral views like this. But if a person cannot be freed from their drawbacks, such persons will be called as bad persons. So essential, you must consider their drawbacks. Okay. So write the definition. Let Z not be a singular point of a complex valued function f of z. Let Z not be a singular point of a complex valued function f of z. Let Z not be a singular point of a complex valued function f of z. Let's stop. If the Lorentz series expansion of f of z, has infinitely many terms, of the form 1 by z minus z naught, if the Lorentz series expansion of f of z has infinitely many terms of the form 1 by z minus z naught, then z naught is called an essential singular point of f of z. Now you start with this example followed by this. Now this is the end of types of singular points. Next concept is residue. Very important. In fact, residues are very useful in complex integration. Suppose we have a function f of z and z0 is a pole of f of z. Z0 is a pole of f of z. Pole means when you go through series expansion of f of z about z equal to z0, it must have at least one term of the form 1 by z minus z0, right? Now, my target is to get the residue of this function at this pole, and that we denote it as res of f of z semicolon z0. Basically, this expression is nothing but residue of f of z at z0. Residue of f of z at z0. So f of z is my complex valued function and z0 is one of its poles. It may have multiple poles, but z0 is one of its poles. So we need to find residue of f of z at z0. This is denoted by res of f of z semicolon z0. And by definition, this is nothing but the coefficient of 1 by z minus z0 in the Lorentz series expansion of f of z, in the Lorentz series expansion of f of z about z0, about z0. So this is the basic definition of a residue of a function at a pole z0. The coefficient of 1 by z minus z0 in the Lorentz series expansion of f of z about z0. That coefficient can be negative values. Sometimes it can be positive values. It can be positive values. Sometimes it can be zeros also. It can be zeros also. Okay. So write the definition. Let Z0 be a pole of f of z. Let Z0 be a pole of f of z. So stop. The coefficient of 1 by z minus z0. The coefficient of 1 by z minus z0 in the Lorentz series expansion of f of z, in the Lorentz series expansion of f of z about z equal to z0. The coefficient of 1 by z minus z0 in the Lorentz series expansion of f of z about z equal to z0 or about z0 is called residue of f of z at z0. Is called residue of f of z at z0. It is denoted by res of f of z semicolon z0. It is denoted by res of f of z semicolon z0. Now, one practical issue in the definition is when you want to find residues of complex valued functions at any one of its poles, if the function is not flexible to go for its Lorentz series expansion. Is my concept clear? Actually, my task is to find the residues of complex valued function. As I mentioned earlier, residues of complex valued functions are very powerful in contour integration. Maybe we discuss in next sessions, but residues are very powerful throughout the complex contour integration. So, when you follow definition, if you are unable to get the series expansion, then how to handle this? So, to overcome this difficulty, we have two important cases to get the residues of any complex valued function at any one of its poles. Okay. So, next concept, procedure to find residue. Next one is procedure to find residue. Procedure to find residue. We have two important cases. Let us see one by one. Suppose f of z is a function and z0 is a pole of order 1. A pole of order 1. That is, they will be called as simple poles. What do you mean by order of a pole? The highest power of 1 by z minus z0. Here I am saying that z is a pole of order 1. That means in the denominator, the highest power of z minus z0 will be 1 only, right? So if z0 is a pole of f of z of order 1, if z0 is a pole of order 1 of a complex function f of z. So case 1, if z0 is A pole of order 1, that is simple pole of f of z, then the residue will be like this: res of f of z semicolon z naught equal to limit z tends to z naught, z minus z naught into f of z. So this is the way to find the residue at simple poles. So here z naught is a pole of order 1 of a function f of z. Poles of order 1 will be called as simple poles. Since I am saying that it is a pole of order 1, the denominator contains only power 1 in case of z minus z naught. So to cancel out z minus z naught of denominator part of f of z, multiply f of z with z minus z naught, and then the rest of the function apply limit at when z tends to z naught. Simple logic. Here I am saying that it is a pole of order 1. Pole of order 1 means the highest power of 1 by z minus z naught in the series expansion of f of z is 1. So z minus z naught will be there in the denominator. To cancel out that z minus z naught, multiply f of z with z minus z naught. So that rest will be something in terms of another function. Then you can apply limit at z tends to z naught. Let us take an example. Suppose we have f of z equal to, suppose 1 by z minus 2 into, for example, z plus 3. Now here z minus 2 power is 1, z plus 3 power is 1. Here 2 comma minus 3 are simple poles. 2 comma minus 3 are simple poles. Because when you replace minus 3, it becomes 0. Now let us find residue at first pole 2. Residue of f of z at 2 is given by limit z tends to 2, z minus 2 into f of z. So therefore this is limit z tends to 2, z minus 2 into f of z is 1 by z minus 2 into z plus 3. So this and this will be cancelled, therefore this is 1 by 5. Similarly, you can find residue of this function at the pole minus 3. So this is given by limit z tends to minus 3, z minus of minus 3, that is z plus 3 into f of z. So therefore this is given by limit z tends to minus 3, z plus 3 into what is f of z? 1 by z minus 2 into z plus 3. So this and this will be cancelled. Replace z by minus 3, you will get minus 1 by 5. So residue at 2 is 1 by 5. Residue at minus 3 is minus 1 by 5. Now look at the magic. When you apply, when you add plus between 1 by 5 and minus 1 by 5, the result will be 0. So here sum of residues is 0. Sum of residues concept is very powerful for contour integration. Okay. So write this case 1 followed by these examples. Suppose if z naught is a pole of order m, a pole of order m where m is greater than 1. Poles of order 1 are handled in case 1. Now from second order onwards, we were discussing in case 2, pole order 2, 3, 4, etc. So if z naught is a pole of order m greater than 1, and f of z equal to, z naught is a pole of order m of f of z, and f of z equal to g of z by z minus z naught whole power m. F of z equal to g of z divided by z minus z naught whole power m. Then residue of f of z at the pole z naught equal to g power m minus 1 of z naught divided by m minus 1 factorial. So that means to differentiate this numerator function with respect to z m minus 1 times. If it is 4, find the derivative up to third order. If it is 7, find the derivative up to sixth order. This is general m. So differentiate this numerator function with respect to z m minus 1 times, and z is replaced by this pole z naught. divided by m minus 1 whole factorial. Okay, let us take an example. Suppose f of z equal to the function e power z divided by z minus 1 whole cube. Z minus 1 whole cube. Now you can see this is in the form g of z by z minus z naught whole power m. What is z naught? 1. What is its power? 3. Therefore 1 is a pole of f of z of order 3. 1 is a pole of f of z of order 3. So therefore to get the residue we need to differentiate g with respect to z 2 times. So what is g of z? G of z equal to e power z. Now here second derivative of z is again e power z only. Differentiate g with respect to z 2 times, again you will get e power z only. But here this is 1 z naught. So g double dash of 1 equal to e power 1, this is e. Therefore the residue of f of z at 1 equal to g double dash of 1 divided by 2 factorial. So therefore this is g double dash of 1 is e. So therefore the value is e by 2. Therefore in this case the residue value is e divided by 2. Write all these points. First write case 2 followed by example. Now let us start classroom workbook from question number 22. Question number 22, classroom workbook. For the function f of z equal to 1 minus e power minus z by z, comma, the point z equal to 0. This is the function 1 minus e power minus z by z. What is the point z equal to 0? Is, options are like this: an essential singular point, a pole of order 0. Pole of order 0 means it's not a singular point. Next option C, pole of order 1. Option D, a removable singular point. So 3 types of singular points were given as options. Pole of order 1, essential singular point, removable singular point, not a singular point. Let us go for series expansion of this. Here z is written in the denominator. This z is nothing but z minus 0. So therefore in the denominator we have z minus 0 terms. So it's a singular point basically. Now let us go for series expansion of this. What is the series expansion of e power z? 1 plus z plus z square by 2 factorial plus z cube by 3 factorial plus and so on. Now therefore e power minus z becomes, replace z by minus z, 1 minus z plus z square by 2 factorial minus z cube by 3 factorial plus and so on. Therefore in this case my f of z is 1 by z into 1 minus of e power minus z is replaced by this series expansion, 1 minus z plus z square by 2 factorial minus z cube by 3 factorial plus and so on. Now therefore this is 1 by z into 1 and 1 will be cancelled. We get z minus z square by 2 factorial plus z cube by 3 factorial minus and so on. Now you multiply this series expansion with 1 by z, it becomes 1 minus z by 2 factorial plus z square by 3 factorial minus and so on. Now when you look at this series expansion, we don't have z terms in the denominator. Therefore the series expansion of f of z, the series expansion of f of z has no terms of the form 1 by z minus 0, of the form 1 by z minus 0. Therefore 0 is a RSP, a removable singular point. I don't have any terms in the denominator once I go through series expansion. Therefore 0 is a RSP, so removable singular point. So option D is right answer. F of z equal to sine 1 by z. So it has 0 as an essential singular point. Now when you look at option B, we have f of z equal to sine of 1 by z minus 2. So just when you go through series expansion of this, throughout the series we have infinitely many terms of the form 1 by z minus 2. Suppose this is actually the series expansion of this is 1 by z minus 2. Z minus 1 by z minus 2 whole cube by 3 factorial plus 1 by z minus 2 whole power 5 by 5 factorial plus, sorry, it is minus, and so on. Therefore, this series expansion has infinitely many terms of the form 1 by z minus 2. So this is an example where 2 is an essential singular point. So option B is right answer. For the function sin z by z cube of a complex variable z, comma, the point z equal to 0 is, function is sin z by z cube, singular point is 0. So options are pole of order 3, pole of order 2, pole of order 1, not a singular point. So let us go through series expansion of this. This is 1 by z cube into sin z can be written as z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial plus and so on. Now they multiply with 1 by z cube, this becomes 1 by z square minus 1 by 3 factorial plus z square by 5 factorial, z square by 5 factorial minus z power 4 by 7 factorial plus and so on. Now here how many terms are there of the form 1 by z? Only one term. So finitely many. Therefore it is a pole. 0 is a pole. But what is the highest power of 1 by z minus 0? 2. Therefore 0 is a pole of order 2. 0 is a pole of order 2. So option B is right answer.